And what we want to know now is what's the highest point that the pebble reaches and how long is it airborne. Notice that each of our two parts of our question end at different times. And so we're actually going to need to maybe make a list for each part here. If I draw little dotted lines to show that it goes up and then turns around, part A of our problem ends here. Part B of our problem ends here. And so we're going to need to divide the problem up into two different sections and maybe make a list for each one of our sections. So in part one, again, since this is just a one-dimensional problem, we're going straight up and straight down. We'll say that delta y equals question mark, and we'll put maybe y top right here because that's going to be the top of our flight. V naught, Vf, A, and T. Now, if you remember a minute ago, we said how down is the positive direction because everything happened down. Well, this problem has an upward component to it. So we're going to stay in an upward frame of reference now, where up is positive, and that's going to have some consequences when we fill in our list. V naught is going to be positive 20 because it's 20 meters per second upward. Vf, we can make a physics assumption about this. Since we're dealing with the top of our flight, we know that the vertical velocity at the top of our flight is 0. It's not mentioned in the question, but because we know that it stops to turn around before it falls down, we can say at this x right here, the vertical velocity is 0. We're still going to use 10 as approximation for 9.8, but look at what we have to do. We've got to put a negative sign there because up is positive, gravity is an acceleration that points in the downward direction, and so this time it's got to be negative. We don't know time. We've got 3 of our 5 variables, so we should be good here. What we want to do here is find the time for this section and then maybe add the time for that section. That's one strategy. Another strategy would be to use the third equation since we don't know the time. So you've got some choices here. I think what I'm going to choose to do is use the third equation just to show how that can be accomplished here. We'll say that Vf squared equals V naught squared plus 2 times A times delta y. And we'll put 0 here, we'll put 20 here. This is always a plus sign just because that's how the equation works. We'll deal with this negative when we do 2 times negative 10 times delta y. So that enables us to write an equation with only one variable. It's solvable. 20 squared is 400. But by the time we bring that over here, that's going to be a negative 400 equals negative 20 times delta y. So 400 divided by 20 is 20. And what we'll see here is that the negatives kind of take care of themselves at that point. We'll divide both sides by 20, and just by coincidence, 20 meters equals delta y. And we'll put a little subscript top because this list of givens applied for the top situation. In order to get the total airtime, we've got to work with both sections or the whole problem all at once. And what I want to model here is instead of dividing it up, we've got another example where we can show how to divide it up and work in 2 sections. I want to use the third equation again, this time to show how everything will go together. We'll put y total here because we want to make a list of givens for the whole flight. Again, up is our positive direction. Now if you start where the stick man is and finish at the ocean, delta y is 54 meters. Yeah, you went up, but then you came back down. Here's your starting point, here's your ending point. The displacement's 54. However, this is a downward displacement. So you've got to put the negative sign in here because displacement is a vector, it has direction. V0 is a positive 20. Vf, we don't know. We don't know the final speed at this final point. Acceleration is negative 10. T, we don't know. We want to find the total time. What we can do is we can say Vf squared equals V0 squared plus 2a delta y. What we're going to be able to solve for here is the final velocity. Once we know the final velocity, we can plug that into the second equation to easily get the total time all in one step. So Vf squared is going to be 20 squared plus 2 times negative 10 times negative 54. Notice that if you don't get your negative signs right, you're going to get a very different answer. So let's put all this in the calculator and see what we get. Vf squared equals 1480, which sounds a little bit familiar. We saw in the prior example, we're going to get a Vf of 38 meters per second. When we look at concepts of energy, we'll notice that kinetic energy doesn't have a direction. So you had 20 meters per second worth of kinetic energy in both these examples, and so by the law of conservation of energy, you should have just as much energy when you smack the water either way. It's kind of an interesting consequence that maybe that's worth filing away. Final velocity is 38 meters per second. What we've got to see then is use our, and that's going to be, now since we had a squared right here, remember your answer when you take a square root is plus or minus. Since this is a downward velocity, this is going to be a negative 38 meters per second squared. We've got to put that negative sign in ourselves due to the fact that this is a downward final velocity. I'm going to come over here, I'm running out of room. We can say that Vf equals V0 plus a times t. We've got a negative 38 as our final velocity. We've got a positive 20 as our initial velocity. Acceleration is negative 10 times time. Now, when we subtract 20 from both sides, we'll get negative 58. My alligator's in the way here. You are not dismissed. Now, we do want positive time, and you notice working things out this way, we will get positive time. And so, we get 5.8 seconds of hang time. You saw me have to catch myself here to insert this negative sign, and when you're dealing with objects that move up and then down that change direction halfway through the problem, there's a lot of concentration that you've got to have throughout the problem. That's why it's always important to draw a picture and make sure your numbers match your frame of reference. Always give your numbers a reasonability check. Our final answer is going to be 5.8 seconds for the time and 20 meters above the height of the cliff. So that would be a total height of 74 meters, depending on how you wanted to express your answer. From the bottom, from the top of the cliff to the height of the throw would be 20 meters, total height of 74. So it's always important to make sure that you understand how the calculations fit in to the frame of reference.